and really it's just about the first half of that section we're doing anyway. But still, there were some that took a few steps. You had to reapply L'Hopital's rule and evaluate, etc. So I'm wondering, do you have any questions there? Yes, Gloria?
Number 15.
So, you know my theory about how kind of a main thing is to look at the types of functions you have and name them, see what they are. The numerator is a what?
Power.
Product.
Oh, is that x times 3?
It's a product. And the exponent is up there. You know, it's not 3 to the, it's not x to the n, it's 3 to the x. So then we have a special rule for that, an exponential function. So this is a product. And there's no algebra that's going to help us out initially to make it simpler, so we're going to have to use the product rule, as long as we determine that, in fact, it is an indeterminate form, right? Got to check that out. When x is 0, 0 times anything is going to be 0, so the numerator is 0. 3 to the 0 is 1, minus 1, 0, so yes, it is an indeterminate form. So it is definitely a candidate for L'Hopital's rule. So it's going to be the limit as x approaches 0. It is important that you write this limit every time, because remember, this function isn't going to equal the derivative of the top over the derivative of the bottom. It's the limit of this equals the limit of that. So now we go about taking the derivative of the top. First function times the derivative of the second function. So that's going to be 3 to the x natural log 3. Or, that's one of our rules of exponents. Okay. This is just something else to memorize, but, derivative of a to the x, here, a to the x natural log, I'm using that. Okay, so then plus the second function, 3 to the x, times the derivative of the first is just 1, so we're good there. Then, now again, take the derivative of the denominator, derivative of 3 to the x, 3 to the x natural log 3, and then derivative of minus 1 is just 0. So there we are. Okay, now, notice that in both of these terms, 3 to the x is a factor. And so it would simplify things if we take a step here before we evaluate again or anything like that. Let's take out a 3 to the x out front. To get this term, it would have to be times x natural log 3. And to get this term, it would just be times 1. And then, of course, it's already out in front of the denominator. So you are able to do this because it's like multiplying by a number over itself, which is just 1. So this is just the limit as x approaches 0 of x natural log 3 plus 1 over natural log 3. Now the denominator is not, there's nothing indeterminate about that. That's just a number. That's like saying e to what power is 3? E is 2.7 something, so it'd be 1 point something small. In the denominator. So we definitely are not going to be able to use L'Hopital's rule again. It's time to just evaluate. If x was 0, we would have 0 times natural log 3 up here, which is 0 plus that 1 over natural log 3. So the answer is just 1 over natural log 3. I'm sorry, I lost track of who asked this. Who was it? Oh, Gloria. Yeah, does that make sense to you, Gloria? Yes. So just one application of L'Hopital in that problem.
Did you get 0 again?
If we're letting x go to 0, so by direct substitution, I'm putting 0 in for that x in the numerator. Yes, yeah, Amanda?
On the second line there, after you've taken the derivative and you have the plus 1,
Uh-huh.
is that the 3 to the x? Because I thought that that would have been, oh, I'm sorry. I was trying to plug in the 0 too soon is what I'm doing.
Right, you can't do it yet.
Okay.
You know, really, it's kind of it's a good general rule to use. As soon as you apply L'Hopital's rule, next step, simplify anything possible. Next step, reevaluate if you can direct substitute or not. And then if you can't, see if you could reapply L'Hopital. Gloria?
Can you just direct substitute in the outright after you apply the L'Hopital?
So up there in the right corner, if you did, we would have 0 plus 1, so there's the 1, over 1 times natural log. Yeah, it would come out right. Yeah, you're right. I'm going to try and find an example, though, between now and tomorrow of where you could get into trouble doing that. Though I might be wrong. It's possible you can always do that, Gloria. I don't know. I have this general principle, I like to simplify whenever I can first. But it's possible, I'm gonna ask Debbie. It's possible that is always a technique you could use and make your work quicker. Yeah, yes, Jen.
Can I see that rule again? The one,
Oh, yeah.
so I can write it down. Yes, thank you.
Is this in our book somewhere?
It is, stuck in the back cover.
Okay, great.
Where? Okay, because the rules are kind of piling up fast, aren't they?
Yeah.
Deborah? Yes. I'm sorry, why can we,
On the second part?
up here?
Yeah, because there's multiplying, the 3x and 3. So how do we just cancel it out?
Well, I did cancel out the 3x there.
I mean, the whole thing, because it's
Oh, all of this with all of this. Oh, that's different.
because we're multiplying.
But there's this, you see. And remember, 7/8 is 2 plus 5 over 2 plus 6. Or even 2 times, in the case to make it like this, it would be like 2 times 4. See the plus in between these? Can I cancel those 2's? If the only way you can cancel something is if, like in this case, see I had 3x times the whole numerator, 3 to the x times the whole denominator. If this had been 6/8 and it's 2 times 3 over 2 times 4, that's when this is like multiplying 3/4 by 1. And that's why it cancels there. It's easier to see it here, I know, than it is over there. But this is, I like to give this example because it makes things a little clearer, I think. In order to cancel, you've got to factor something out that's times that whole numerator and whole denominator. It's tempting, but you strain yourself. Okay, What else? Are there others? Gloria, is your hand sort of up?
Do you mind if I ask a question on the point?
No, that'd be fine.
She was like, you should do all my
Okay, 29 says, okay, that's not one I assigned, right? On 3-5? I mean, we can do that, but I did assign 25, but I don't think I assigned 29. 39 I assigned. Yeah. Okay. Others. So, y'all know, this is the time to really dig in. We've got now quite a few formulas, and they all have to be used in practice, so they belong to you. You know, you need them to belong to you. And I would take the page of the formula and I keep it right in front of me when I did the problem, and work the problem and use what formula I can, and then I'd get out a clean sheet of paper and put the formula away and see if I could use it again, you know, to make sure you own it. In some classes, you know, we can give formula sheets and stuff. In this class, the general feeling in the math department is that they're really important formula and you need to know them, and so we can't give formula. Yes?
I have trouble knowing on these when to use the natural log. What indicates that that's, hey, you know, don't just continue with your product rule or whatever, you need to indicate that there's a
You
natural
mean
log.
when to use logarithmic differentiation?
Yes, I'm unsure on these. Where
Right,
to
I'm
use them
gonna
and
tell
when.
you, I know, I would be too. I'm gonna tell you, at least if it's a quiz or a test, I will say, use logarithmic differentiation, so you know to do that. Now, if the problem initially has logs in it, like for example, if we're looking at 3, I guess the square, where does this get come into, oh yeah. Right, let's say you're looking at 3, and you have a problem, I don't know, this might be one, there was one the other day that I did and I forgot to use the rules of logs. And it made it longer and hairier. It's not that it's wrong, but you know, you're just smart to use them when you can. When you look at number 9, the natural log of a quotient, there does need to be something in your head that says, oh yeah, that's the natural log of the top minus the natural log of the bottom, and then all of a sudden things are easier. In number 11, you do have to figure out, you have to see that natural log. It will have to be natural log no, it could be LOG also, but pretty much natural log is what's going to show up in the class.
Okay.
And so you'd see that is the natural log of a product, and the second thing is going to be to the 1/2 power, and the 1/2 is going to come out front, all that stuff. If I had to sign 13, absolutely for sure on 13, you need to use the laws of logarithms or it's a mess. So yeah, you need to kind of school yourself. If it's already in the problem, ooh, could I make that simpler? But if it's not in the problem, you won't have to worry about it, because I will say use logarithmic differentiation. If I want to. Did I answer?
You did. I do have one more though.
Okay.
So whenever you add the natural log to these, when you're taking the limit, is it a rule that you are always adding it after something like an exponent? Like if there you see an exponent, is that key that there's going to be a natural log there?
Well, it matters what is the variable and what is not the variable. You see here, 3, see how in the rule A, you know how Stuart considers A and B and C, they are constants.
Right.
So a is a constant number to the x power. So the variable is up in the power. This is way different from something like x to the n, where you're just using the plain old power rule. Now the variable is down here, and n is some power, where you could say n times x to the n minus 1. Way different, yeah. So but you get used to how different they are once you work with the formula. But it does sort of take that. Okay, others? Okay. So, I want you to make sure and do 17 and 21, if you haven't done them yet, because they both have multiple applications of L'Hopital's rule, and but nothing tricky or anything. You just have to keep simplifying, applying, you know. All right. Okay, this starts chapter 4. Applications of differentiation. Now, this is something that is traditionally, some classes in calculus, they don't focus on the trig stuff quite as much, and they don't focus on proofs quite as much, and sometimes L'Hopital's rule is not included in a calculus 1 class. We do those here, though, but what we're about to do is something everybody includes in calculus 1. So we're going to look at ways to optimize, ways to do things the cheapest, the quickest, the most effectively, and optimization techniques really hit their peak in World War II, when we found we could not just run our factories in the way that we had always done, assuming we have plentiful workforce and didn't necessarily have to do things the most efficient way. But once we got to be World War II, there were certain things that we needed our factories to do, certain numbers of goods that needed to be produced, and we didn't need to waste any money or our person power on doing it. And so optimization really flourished in World War II. And so if you look on page 203, it has some bullets here. These are all things we're going to work towards answering. For example, if we're manufacturing a can, like you know how many cans are manufactured for sodas and other kinds of drinks, we want to minimize the manufacturing costs. So think about, that's going to mean minimizing surface area, for example, so that it encloses whatever liquid is in there, and yet we're not using more metal than we really need to. You've noticed a lot of times, like on the sides of cans, they've gotten really pretty thin, and on the lid, it's got to be a little thicker because you're cracking the lid, it has to be stronger for that. All kinds of things are done in order to minimize manufacturing costs and produce bunches of those cans. What is the maximum acceleration of a space shuttle? So, we put humans in space shuttles, right? And so it's not just the machine, but what can we withstand? So we need to know what's the maximum acceleration that people can live through when riding on a space shuttle. What's the radius of a contracted windpipe that expels air most rapidly during a cough? Now, honestly, I'm not really sure why this is, but there must be a reason that they said this. But it's not like you could make a decision, I'm going to contract my windpipe to a radius of so-and-so so that I can cough most efficiently, but I don't know. I don't know why they asked this. How far should you stand from a painting in an art gallery to get the best view of the painting? So there are even things like that are considered. Now, this is a consideration if you had a gallery where you exhibited paintings, and you're building it from the ground up. You know, you don't want the hallways to be so narrow. If you do narrow hallways, then you have more hallways, you can put more paintings up, right? But if you have to stand looking at a painting like this, is there any way you're gonna get kind of the overall idea of what's in it, right? And you know, what height should they be mounted so that you stand at a certain distance and you can take it all in and think about it and whatever. So there are all kinds of things that this is applied to, the study is applied to. Okay, now in this book they talk about something called an absolute max. In other books they might call it a global. So anyway, the absolute, I'll probably call it both, or global max of f at c implies f of c is greater than or equal to f of x for all x in the domain of f. And the absolute or global min of f at c implies f of c is less than or equal to f of x for all x in the domain of f. So this is how we would write these things out symbolically, but I mean practically it should make some sense. So yeah, Jennifer?
What is that it's on both of them, but what is the very last? Yes.
For all.
Okay.
For all x in the domain of c.
Okay.
Okay, so absolute max means it's the highest thing. Absolute min means it's the lowest thing, because you guys, you see min of f. F of x is a y thing, right? So we're talking about height. You never say the words min and max to apply to x. You say the words min and max to apply to y, a height. So I'm going to write in here after absolute global max, I'm going to call this highest, and absolute global min, I'm going to call this lowest. Now, it also, you can call something a global max and have other things be that tall, but they just can't be taller than it. You see, because I put equal to here both times. So other things can be that tall, just not taller. Stacy?
So are you saying a local max can be the same as the absolute max, but just not taller?
That's correct. That's correct. And you can call it an absolute max. You can call it a local max as well. By default, it is also a local max. Yes.
Is that a new symbol that I haven't seen yet?
Where?
The, for all f of x.
She just hadn't used it since chapter 1. She had used it a lot.
Yeah, I think I had it on an initial list way back, but I've used it a lot.
I've got it.
You can prove me wrong?
Yeah.
Well, that's not going to be a new thing, you know. Okay.
Yeah, I don't see it. What's it called?
For all. Okay. Now I've got some pictures I want to show you so we can discuss these ideas with some pictures. So here we go. Let's see if we can. All right, now this is y equals the cosine of x on all the real numbers. So we know that it has a global max of 1. Notice that Jennifer named me a y value, didn't she? Okay, so you don't have to specify that y is 1, because when I said the word max, I knew that's what we meant, and you did too. Okay, now, so you can say that the cosine of x has a global max at multiples of integer multiples of 2 pi. Because every 2 pi, it hits one of its maxes, doesn't it? And you can say cosine of x has a global minimum at, yeah, it looks like odd multiples of pi, doesn't it? Does anyone remember what the mathy way to say oddness? 2k pi plus 1. So get an even thing and add 1 to it. Right? 2k pi plus 1 would force it to be an odd multiple of pi. So the global, we can also call them local mins, occur at those odd multiples of, you can always also write out odd multiples of pi. Yeah. Okay. Then let's look at y equals x squared on all the real numbers. It has no max, no local maxes, no global maxes, certainly, because this is happening, right? But it does have a global minimum at you can, okay, here's correct things to say. You can say it has a global minimum at x equals 0. You can also say it has a global minimum of 0, because 0 is also the y value, isn't it? Yeah, both of those are true.
Can you give a point, like 0, 0?
You can also give the point. It has a global min at 0, 0. That's also correct. In just a minute, I'll give you one way to say it that would be incorrect. Here, kind of everything's at x is 0, y is 0, so it works out just fine, you know. But I'll give you, well, like for example, go back to the cosine of x. I could say it has a global minimum at x equals 0. Sorry. I could say it has a global maximum at x equals 0. I could say it has a global maximum of 1. And I can say it has a global maximum at 0, 1. But I cannot say it has a global maximum of 0. Because that's not true, because then I named the x value and the maximum is actually 1. I can say at 0, 1, yes. But if you ask for the max, you should name the y thing is the main thing to name. You may also name the x if you want. Yes?
So what is the difference between the local and the global value? Or is it the same?
Isn't that a good question? There's really no difference up there, and there's really no difference here, but there will be a difference, and I'm going to show you. Good quiz. Great lead-in. First, I'm going to show you this, though. Is there a global maximum of y equals x cubed?
No.
No. Is there a global minimum of y equals x cubed?
No.
No. Absolutely. Okay. Now, to Maria's question. Let's look at this guy here. So, I've got a polynomial. It is a 4th degree polynomial. That they have a possibility of having 4 roots, but one of its roots is a double one right here. You know, when they come and hit the x-axis and bounce back up, that's like a double root. It's got an x squared in it. Okay, so it's not good. What I mean is, this one is not going to turn around any more times. Now, and by the way, I've defined it in a certain way. On a closed interval, from -1 to 4, it's defined on, of course, those are all x values from -1 to 4, and I've got hard dots there and there. Now, is there a global maximum?
Yes.
Yes.
Yes. What is it?
-137.
-137 is a correct thing to say. It's also a correct thing to say its global max is 37. Yes. Is it correct to say its global max is -1? No. It is though correct to say if you named that -1 as an x value, if I said there's a global max at x equals -1, that would be, I would count that correct too. It might just mean you didn't have time to calculate the y value that goes with that, but you know it happens when x is -1. That's correct too, but you had to name x equals -1. Okay, now, here at x equals 0, Maria, there is a local, do you know? Because it dips there, that's going to be a minimum, okay? So, but you have to restrict the neighborhood around that x value, you know, if you want. Well, we can call it a local minimum no matter what. But what it means is, for a little neighborhood around x equals 0, this is the lowest thing going. Okay, and there is a local max at 1.5. Yes, at x equals 1, at 5, or at 1.5. All those are correct. Yes, Viola.
Sorry, I was talking to myself. I
Oh.
was just wondering if like, does local just mean it's not exactly the lowest point? Like,
Not function wide, it's not the lowest, but in its own little neighborhood, it's the lowest thing.
Okay.
That's right. That's right. Good. Okay, now do you see, like at the point 2, -8, it's not possible to build a neighborhood around this x equals 2 so that -8 is either the highest or the lowest thing, right? Because immediately on the right you go lower, immediately on the left you go higher. So that's not a candidate. But over in here, when x is 3 and y is -27, what would you call this? It's an absolute min. It's also, local min is correct too, but it's also the lowest thing function-wide, isn't it? Okay, so both of those are correct. Yes. Okay, now, what would you say at x equals 4? What would 32 be? Local max. Now, you see there, on the left, any neighborhood to the x equals, anything to the left of 4 is going to give you lower stuff than that, so making it a max. And there isn't any neighborhood to the right of 4 because of the way I define the interval. If I had opened it up to all real numbers, it continues to go on up on the other side, so there would be no global max at all. But since I cut it off at and just went to 4 here, I could say that there is a local max of 32. So this has lots of different things going on here. What else can I say about this? I mean, polynomials have them all the time. Oh yeah, let's notice this. This is kind of going to be the big result of this section. What appears to be the case to you? Now forget about the endpoints for just a minute. And look at these other spots where we have local and absolute maxes and mins.
Continuous and differential.
What'd you say?
It's continuous and differential.
It's a polynomial. It's differentiable everywhere in there. But can you say anything about the actual derivative at those particular local minima and maxima? It's 0. Wouldn't we have a horizontal tangent line at each one of those places? Okay, that is going to be the core of what is in this section called the extreme value theorem, that says if I have a continuous function on a closed interval, so no cuts, holes, or jumps, and it's differentiable on that closed interval, then all the maxima and minimum that you can possibly find will occur either at the endpoints or where the derivative was 0. So this, you can graphically see this right here going on. If I wanted to know what's the absolute max, absolute min on this interval, all I would need to test are the endpoints and the places where the derivative is 0. Now, you see how this would fail us in the case of an absolute value function. Remember how the derivative does not exist at that vertex? And yet a minimum is formed there, an absolute minimum, right? So if the extreme value theorem is not going to work out for us if the derivative doesn't exist. So we need the derivative to exist, and we need continuity on a closed interval. Yeah. Okay. Yeah. Okay, so first we've got Fermat's theorem. Now, Pierre de Fermat was a French mathematician, and he was real quirky and real famous. And you might remember that there's a mathematician at Princeton University that just recently proved Fermat's last theorem. It was huge, mega proof that took just a very long time. But he did actually prove Fermat's last theorem, I don't know, within the last 10 years. I don't exactly remember anymore when it was. But anyway, he had this theorem. He believed this thing was true, and he couldn't prove it. But he also had this fear that he would die by drowning. So he used to go between France and England, over the channel by boat, fairly frequently, and he hated it because he thought he'd drown someday. And so before he left France for England, he would write friends of his and say, I found it, I've proved my last theorem, and I'd write it to you, but it's too large a proof to put in the pages of this letter. And then he'd mail that letter. Then he'd get on the boat and go across the channel, and then he'd send retractions when he got there safely and didn't drown. He would send his friends letters. Oh, well, I found a flaw in my proof. So apparently he did this several times. But he wanted to prove it really badly, and he tried, but it was a mega huge proof that really has only now recently been done. Now, this is what he said, and it's something we just noticed in our little polynomial over there. If f has a local max or min at some value c, and if f prime of c exists, then f prime of c is 0. So picture that polynomial we just had, where we found the local maxes and mins, and we saw the derivatives, and they were 0 at those particular places. Now, the converse is not true. Just because you know the derivative somewhere is 0, that doesn't necessarily mean that it's a local max or min. And here's the thing. Here's why. Look at y equals x cubed. Okay, we got power rule here. If you were to take the derivative of y equals x cubed, what would it be?
3x squared.
3x squared. Okay, set 3x squared equal to 0 in your head. What does x have to be?
0.
0. Okay, so the derivative is 0 at 0. So, I mean, you see how this thing kind of flattens out there? So the derivative is 0 right here at x equals 0. However, we don't have a max or min there, do we? So that's how it can, the converse is not true. Okay, so comments. 1, the converse is not true. And an example is y equals x cubed. No max or min. Okay, number 2. The other comment is there can be an extreme value, where f prime of x does not exist. Like what I mentioned, f of x is absolute value of x. This has an absolute min at 0, 0. But f prime of 0, as we have seen before, does not exist because of that pointy thing right there at the vertex. Therefore, 3 balls. We begin looking for extreme values where either f prime of c is 0 or f prime of c does not exist. And I'm going to put a little addition here, or endpoints. If you have something like that polynomial that I showed you that's defined on a closed interval, then we would look at those endpoints too. Remember, the absolute max of that thing was up at one of those endpoints. Okay. Now, I've got a couple of pictures here, and this, I'll just show you this, and then that'll be it for today. Oh, absolutely. Thank you. Because I want you to see this, I think maybe you get the requirement that the derivative is 0, and I think you probably get the fact that sometimes if the derivative doesn't exist there, that could be a min 2, like at the absolute value. But the other condition I want to address is continuity, how important that is. Okay, are we ready to go to the pictures?
Yes.
Okay. Okay, now, check this out. Let's suppose I take this particular function, and this looks like y equals 1 over x, but shifted 2 units to the right. So it'd be like, this would be f of x equals 1 over, let's see, I've got to shift to the right 2, so it'd be x minus 2, but also it's up some, isn't it? So plus 1, yeah. That's what that would be. Okay. So now, suppose I only defined it from x equals -2 to x equals 4. So chop off the domain and just look at this piece. Now, this is nice and smooth, and this is nice and smooth, but here's a big old hard vertical asymptote right in the middle of it where it's undefined. Now, does this have any, taken as a whole, does it have a global max? No. Taken as a whole, does it have a global min? No. Does it have a local max?
Yes.
So, endpoint right here, it does, right? And so we know we got to look at these endpoints. And does it have a global min? Well, right there, at that endpoint, right? But if we did not require continuity, hold on just a minute, I sort of lost my train of thought.
You meant
Oh,
local.
here it is.
Right?
We need continuity on a closed interval. The extreme value theorem, which is the next thing we're going to do, that Fermat's theorem is like a prep for, says that f attains an absolute max and an absolute min somewhere in that interval, either at the endpoints or in between. That's not true here. Function-wide, there's no absolute max at all. Why? It jumps. It's not a continuous function. So you must have continuity on a closed interval for this extreme value, for there to be guaranteed absolute max and absolute min. Yes?
Would one of those be the local max and local min, or could they both be both at the same time? Can they both be the local max and?
You can have more than one local max and they can attain the same height. Actually, there's a
Is that
horizontal
yours?
asymptote there here at y equals 1. So they're not quite at the same height. But we could construct something that was.
Okay, so you don't have to worry about if the arrow's pointing up, that one would be a minimum. It doesn't work that way.
Oh, well, no, because these could go further down here and further
Okay.
up there. I mean, they can be real fancy. But function-wide, because of this action right here, there's not ever any absolute max. Okay? And because of this arrow right here, there's no absolute min. And the extreme value theorem, see, read the word extreme, that's not just looking for local stuff, that's saying absolutely the highest thing going in this function. Is there a highest thing going here? Nope. Maria?
But talking like locally, the 1 and the -2, that would be a max because to the right it's going down, correct? And then the
This
one
would be a
a
local
minimum.
min, and this would be a local max.
Right.
Correct.
Okay.
Yes.
And you indicate that because the arrows, or the continuous line.
Indicate the local stuff.
Yeah, because it looks, I mean, you know, that dot is smaller or shorter than that dot, so it kind of looks like that would be the smaller and that would be the taller, but.
Actually, that's kind of immaterial in this case, because when I look at this, I'm only looking at a neighborhood around it. You know, it has to be the highest thing in a neighborhood around it. Remember, when we had this picture over here, this is a really good question to consider. I called this a local max. I didn't care there was a local min. I didn't care there was a lower one. Just in a neighborhood of it, it's the lowest thing. That's the crucial deal. And in the second one, now this is kind of strange, I know. Looks continuous, but we remember the deal was on a closed interval. And I didn't do that. I put a parenthesis at -3. So that means when x is -3, we've got an open circle there. Now, you know, theoretically in math, the deal is this gets higher and higher and higher and approaches this height of 1, 2, 3, 4, but never gets to 4. There's this is sexist and crummy, but still you'll remember it. The difference between a mathematician and a statistician is this. Let's say there's these two men, and there's this beautiful woman they both desire. And so they're given the opportunity to walk closer to her by every day they can travel half the distance to her. And then half again and half again. So the mathematician rejects the deal because he says, well, if I'm only going to get to go half the distance, I know I'll never get to her. So doesn't take the deal and walks away. The statistician says, well, I may never get to her, but I'll get close enough. You know, so, I mean, that's different. This is getting closer, closer, closer to a height of 4. It never gets to 4, but theoretically there is no highest value that y ever attains, because when you name it, like 3.999, you can get closer to that, 3.99999. You see what I mean? Okay, that's it. I'll see you tomorrow.